Not yet. This one, huh?
Yeah, ma'am, that one. Yes.
Yeah. So actually, I haven't get the co-host access yet, so I can't able to share my screen. But I'll brief you how we can solve this
Okay.
question.
Okay, ma'am.
So 10 friends in a college decided to have a night party at the home of one of them. So unfortunately, at D-Day, the government closes many of the routes of the city. So the below graph shows the location of their homes and the open routes as the graph G is equals to V comma U. So that means here the vertices are the homes of every friend, and the edges are denoting the open roads among their homes. So that means if there is an edge, so then we can travel from someone's homes to some another person's home, right? So V is a set of nodes and E is a set of edges representing the open routes. Now here, the second question says the possible place for the party is, right? So if we want to host the party, so we want that every vertex can reach up to that vertex. So ultimately, what we want to find, so we want to find out a vertex where we can find a path from every other vertex. So for example, if you decided to throw the party at Ritu's house, so you observe that there is no incoming edge to the vertex Ritu, right?
Ten.
There is only one outgoing edge. So obviously we cannot throw a party at Ritu's house because no one will come there, right? So that means Ritu is discarded. Similarly, if we throw the party at Joe's house, then Ritu can come, and similarly Vaishali can come. Uh, Naya also can come, and but Shiva cannot come, right?
Huh.
Because
So,
Shiva,
yeah, yeah,
on
yeah.
Shiva we don't have any what you can say
Hey.
outgoing edge. So Shiva cannot travel to anyone's house. So the possible candidate might be Shiva, because if you want to throw the party, then everyone should be there. So, but Shiva cannot move or cannot go to anyone's house because there is no outgoing edge from Shiva. So I guess the answer should be Shiva. And let's think that if I mean the other persons can also reach to the Shiva's house, because Naya can reach,
Yeah,
Vaishali
there are
also can
edges, right?
reach.
Yeah. Mm-hmm.
Yeah, we have a sufficient number of edges over the left hand side of the graph. So that means we should throw the party at Shiva's house. So the answer should be Shiva.
Yeah, Shiva's house.
Right.
Okay, question number 3 and 4 also.
Yeah. So question number 3 says let V1 be Kriti, Shiva, Naya, and E1 is equals to E intersection with V1 cross V1. So that is E1 is a subset of edges of G with both endpoints in V1. Okay, so choose the correct option. So if G1 is equals to V1 comma E1 is an undirected graph. So here what you have to do, you just have to take the vertices, these three vertices, and whatever edges are there in these three in between these three vertices. And if every edge is a two-sided edge, so that means you can travel from one vertex to another vertex, and also you can travel back. So if such kind of possibility is there, then that will be an undirected graph. Okay, you're getting my idea.
Yeah, yeah,
So
yeah.
for undirectedness, it's easy. Now, similarly, you can find the cycle, because see, there are only three vertices, so the graph won't be much larger. So if we consider Shiva, yeah, so it's a very simple graph, right? There are only two edges. It is not an undirected graph, it is a directed graph, because we can travel from Naya's house to Shiva's house, but we cannot travel back. So obviously, it's a directed graph. There is no cycle,
Yeah, yeah.
right?
Yeah, yeah. Yeah.
And it will be a graph and it will be a directed graph. So that's why option number 4 is correct. Now, question number 4 says if Joe wants to have a party on his house, then at most how many members can join the party? So that means we ultimately have to find out the number of paths between other vertices to the vertex number Joe, right? So we can, Ananya can reach to Joe's house, right? Kareem also can reach, Abhi also can reach, Ritu also can reach, Ruby also can reach, Vaishali also can reach because we have two-sided edge, right?
Yeah.
Naya
And
also can
Mia.
reach,
Yeah.
right? There are
Yeah.
only two persons who cannot reach to Joe's house. So the answer will be 1, 2, 3, 4, 5, 6. Right? And Joe, including Joe, there will be 8 members in our party.
Oh, so including Joe, you have to include Joe also.
Yeah.
Yeah, okay. Yeah, yeah. Okay, thank you.
So yeah, we can call a cycle a graph, because there will be a graph which ultimately look like a cycle. But in a graph, there are cycles. So I don't understand what you are saying. What is a cycle? We can call a cycle a graph means.
Can
So
we
in previous session, yeah.
can we call
What's your question?
can we call a circle a graph?
Oh, circle. No. Then what will be the vertex in the circle?
Infinite.
Yeah, if you take infinite vertex, then obviously. But in graph theory, we generally don't talk about infinite vertices, right?
Yes, ma'am.
Okay, so let's start. So in the last session, we have talked about BFS process. Now we'll start on DFS. So what is DFS? So as like BFS, DFS is also a strategy to find out the answer of reachability question. So that means, can we travel from one vertex to another vertex or not? But in BFS, what we are doing in BFS process, we explore every vertices level by level. Level by level means we started with some vertices, we go to their neighbors, right? And then we pick one neighbor, explore their neighbor, another neighbor, explore their neighbor, and another neighbor, and then explore their neighbor. That's the strategy in BFS. So that means we are doing every exploration level by level. So in the zero level, we have one vertex. In the first level, we have neighbor of that particular vertex. In the next level, we have neighbors of that particular vertex, right? But in DFS, we have some kind of aggressive strategy. So that means here we'll go in one direction up to that point where we cannot get any new vertex. Okay. So as like in BFS, in DFS, we collect the vertices of, we collect the suspended vertices. Now, what are the suspended vertices? I'll let you know. So we collect the stack of suspended vertices. So here, for collecting suspended vertices, we use the stack method of collecting a sequence. So as like in queue, so queue is based on first in first out principle. So whatever we take in first in queue, we have to explore that vertex first. But in a stack, we use first in last out principle. So stack means, for example, if you make a stack of your books, then whatever book will be at bottom, that book we can access only at the end, right? So this book we will we as we are making the stack, we'll first put the book number 0 here, right? This book will put at the first place. But if you want to access this book, that is only possible when you we can only access this book at last only. So that's the principle of stack, that first in last out. Okay. So here we collect the stack of suspended vertices. So what are the suspended vertices? So in DFS process, we start exploring a graph with a one vertex. Then we suspend the exploration of that vertex and go to its neighbor. Any neighbor you can choose here. So you go to that neighbor and then again suspend the exploration of that neighbor and go to its neighbor's neighbor. Okay, so let's see what is DFS process. Okay, so let's start DFS process from vertex number 4. So again, as in BFS, we also list out the visited status. So initially it will be false. So as I mark 4, as we visit 4, we will change the status from false to true. So now visited status is true. And now what we do, we will suspend the exploration of 4 and add this 4 into our stack of vertices. Okay, so we'll suspend 4 and add that 4 into a stack of vertices. And now we will explore any neighbor of 4. So now there are 3 neighbors of 4, right? So we have 3 neighbors. We have 0, we have 0, we have 3, we have 7, right? So we can choose any one of them. It's up to you. But see, as our convention says, that choose the least number. So what is the smallest number in these 3 numbers? The smallest number is 0. So that's why we took 0. So now we will suspend the exploration of 4. So as we suspend any vertex, we will enter that in our stack and then start the exploration of 0. So as we explore 0, again we have some path, or again we have some edges which will connect us to some unvisited vertices, right? So the vertex number 1 and 2 both are unvisited. So now we will suspend the exploration of 0 and explore another neighbor of 0. So now there are two neighbors, 1 and 2, but again we'll take the least number. So that's why we'll take 1. So now we'll suspend 0. Since we are suspending 0, we'll add 0 in our stack and explore 1. As we explore 1, we also change the visited status of 1 from false to true. Right. Now again from 1 also we have a path to which lead us to a new vertex. What is a new vertex? New vertex means unvisited vertex. So here 2 is the unvisited vertex. So that means we can now also we can suspend the exploration of 1 and go to vertex number 2. So as we now we will suspend the exploration of 1 and go to vertex number 2. So as we suspend the vertex number 1, we will add that vertex into our stack and explore the vertex number 2. But observe here that at vertex number 2, we don't have any edges which will connect us to a new vertex. New vertex means any unvisited vertex. So that's why here we have to stop and we have to backtrack. Right. So now what we'll do, we'll backtrack. So that means we now suspend the exploration of 2. Not suspend, we will backtrack from 2. So as we backtrack any vertex, we will remove that vertex from our stack. So when we enter a vertex in our stack, when we suspend it, and when we remove a vertex from our stack, when we backtrack. Okay. So as we backtrack from 2, we'll go to 0. We will go to 1. As we backtrack from 2, we'll go to 1. So that means we backtrack to 1. So as we backtrack to 1, we will remove that 1 from our stack of vertices. Okay. Now again from 1 also we don't have any new edges which will give us some new vertex, right? We don't have such kind of scenario. So that means we have to backtrack from 1 to. Okay. So now we have to backtrack from 1. So that means we are backtracking to 0. So again we will backtrack to 0 and remove that 0 from our stack of suspended vertices. Now we again from 0 also we don't have anything new. So that's why again we'll backtrack from 0 to 4. So as now we backtrack to 4, we also remove 4 from our stack of vertices. Now from 4 we have choices, right? Now from 4 we can go to 3, we can go to 7. Again we'll choose the least number. So that means from 4 we will go to vertex number 3. So now we have to suspend the exploration of 4. And as we suspend the exploration of 4, we have to enter this 4 into our stack of suspended vertices. So we suspend the exploration of 4 and go to the vertex number 3. And now we will explore 3. Now again 3 has 2 vertices, 2 neighbors, 5 and 6. So you can choose any one of them. But again we will choose the least number. So we'll now we will suspend the exploration of 3 and go to the vertex number 5. Right. As we suspended 3, we will add 3 into our stack of suspended vertices and change the visited status of vertex number 5 from false to true. Okay. Now from 5 also we have a way to go to another vertices. So we can go to 7 and we can go to 8. So now we'll go to 7. From 5 we have 3 choices. We can either go to 6, 7 or 8. Yes, 6 is also there. So again we'll choose the least number. So we'll go to 6. So as we go to 6, we have to suspend the exploration of 5. So that's why we will enter 5 into our stack and go to 6. But at 6, we have a situation that we don't have anything new here. Anything new means we don't have any edges which will connect us to some unvisited vertices. So that means we have to backtrack from 6 now. So as we backtrack from 6, we'll go to 5. Now here observe that as we backtrack, we cannot go to 3. Okay. We have to go to 5 because we reach 6 from 5. That's why from here, if you backtrack, then you have to go to 5, not to 3. Okay. So now we'll backtrack to 5. But as we backtrack, again, I'll say that we have to remove 5 from our stack of vertices. Now from 5, we have new vertices. We can go to 7 or we can go to 8. So now we'll go to 7. So that means we'll suspend the vertex number 5, go to 7. So as we suspended 5, we'll enter it in our stack of suspended vertices and change the visited status of 7. Again, from 7, we can go to 8. So we'll go to 8 and we can go to 9. But again, from 9, we don't have anything new. So we'll keep backtracking. So as we backtrack to 8, we backtrack to 7, we backtrack to 5, then 4, then 3, and then 4. So now we have backtracked all the vertices and our stack is empty and the whole and every vertex is now visited. So now here our DFS process will stop. Now as like DFS will stop when we backtrack every vertex. Okay, so this is a particular DFS process. Is there any doubt in this process? Anything? This is not clear. It's just a process. Just go through it. You'll understand the idea. In BFS process, in DFS process also we can extract one tree. So what is a tree? So tree is nothing but a connected acyclic graph, or you can say a minimally connected graph. Means in that graph, if you add one edge, it will create a cycle. If you remove one edge, it will disconnect the graph. Such kind of graph is known to be a tree. As like in BFS process, we extract one tree from the graph. Same thing we can do here also. So here we just have to look at these steps. So what are the steps we have done? So here first we started with 4. So the root will be 4 for us. Then from 4, we go to 0, right? Then from 0, we have gone to 1. And then from 1, we went to 2, right? Now from 2, we have backtracked to 0 and 0 to 4. Now again from 4, as we suspend 4, we explore 3. So that means after 4, we reach to 3. From 3, we reach to 5. From 5, we reach to 6. But again, we have to backtrack. So as we backtrack, we go to 7. From 7, we go to 8. And from 8, we go to 9. Okay. So now this is a DFS tree. So this is a tree we obtained as we apply the DFS process. So how we are making the tree? We are choosing those edges which are used in our DFS process. Okay. So that's how you can build a DFS tree. Is that fine? Any doubt?
Okay, TFS tree is kind of just tracking the path we have gone through.
Right. Tracking the path we are doing.
And it is just a notation that we have to take the smaller value. In real life, we can take any random if it's not about numbers.
It's not about the numbers. We can take any number, anything. Since our convention is that we have to take the smaller number because it won't spend, we don't have to spend too much time on thinking that which number we should pick, right? So that's why we have made this convention.
So with making different choices of numbers, won't it we have a larger set of ambiguity, because in this question itself, if we flip a little bit, then the final graph may vary, I think.
Correct. Final graph will be different. This is not, this thing won't happen in BFS process. Because in BFS process, we don't have actually choices. We have to explore neighbors one by one only. Yeah, but there we have choices that we can choose any neighbor front and back. That means we can choose, instead of 4, 5, 8, we can choose 5, 4, 8. Right? So these only choices we have. But in DFS also we can choose any neighbors, whatever neighbors you want. Okay. Now let's go to directed graph.
And ma'am, with this both ways we have to explore the graph, which one would be kind of faster to reach the target that we may assume the graph has?
So actually these two methods work in a very different scenario. So for example, if you want to find out a spanning tree, what is a spanning tree? We will discuss it in week 11. So that will be a tree. Or if you want to find out the shortest path between any two vertices. Now this problem you can solve using the BFS process, but this problem you cannot solve using the DFS process. Okay, and why is this so? You will understand in week 11. And if you want to find out the cycles in a graph, so suppose you have a directed graph, or if you have an undirected graph. So for undirected graph, using BFS, DFS, using both methods, we can find out the cycles. But in a directed graph, for finding the cycles, the DFS method is much more helpful. Okay, so both has their particular, they will solve very different kind of problems. So there are problems which can only be solved by DFS process, and there are problems which can only be solved by BFS process.
Excuse me, ma'am.
Yes.
Ma'am, BFS process, we were able to find the connectivity that whether if there is edge between two numbers, like is there an edge between two numbers. But here, if we look at the tree, So
Hmm.
actually it becomes difficult to find, like there we had a thing that if the first like if 2 belongs to the first stage and 3 belongs to the second, then there can be a connectivity between the two. But here, as you drew that tree, there was an edge between 4 and 7, but that cannot be actually interpreted by
Identified by the tree. Correct,
yeah.
correct. So
So ma'am,
this
like,
thing we cannot say.
okay, so could you please give some more examples, like what kind of situations, in what kind of situations we'll need BFS and DFS?
So yeah, see what kind of there are problems, right? So that means if you want to find out the shortest path between any two vertices, then you will need BFS tree. And if you just want to find out the cycles, then you need DFS process. So in our course, we just have these two problems related to DFS and BFS. Okay, so either you will get question on DFS, BFS, like the following tree can be a BFS tree or DFS tree of the graph or not. So yeah, so because of our restrictions, since we haven't gone through very deep connection of DFS and BFS, so I'll tell you that there will be fixed a kind of question. So first question would be that possible edges, right?
Yes, ma'am.
If there is a possible edge between two vertices or not, we have to judge that just by looking the BFS or DFS tree. Okay, so in BFS process, it's kind of easy. In DFS process, we have to observe some more things. I mean, that will be easy, but if you just remember the DFS process, I don't have example for that. But yeah, this is a one kind of question, and it mostly asks using the BFS tree only. It is very rare scenario where someone asks about DFS, because in DFS we have so many graphs can possible related to one particular DFS. Okay, so this is one problem. Second problem is they will give you a graph and then ask which of the following can be a BFS tree, BFS or DFS tree, right? In that case, you just have to apply the BFS and DFS process and extract. And again, you have to consider the possibilities of neighbors. So if you choose this neighbor, then what will be the tree? If you choose that neighbor, then what will be the tree? Okay. So this is the second kind of graph, second kind of question. And third kind of question they can ask, that they will give you a BFS tree. They will give you a BFS or DFS tree and then ask for a graph. So what is a possible graph? Then again, on every graph, you have to apply BFS and DFS process and observe that this, after applying BFS, DFS process, what are the tree we are getting. Okay, so these three kind of question only can ask from BFS and DFS now, because we don't have that much information. And the fourth kind of question can be about the forward, backward, and cross edges. Okay, so forward, back, and cross edges, which we will cover in this particular session. Okay, so these are the four kind of questions only you have to prepare from DFS and BFS. Is that fine?
Okay, ma'am. And ma'am, in DFS, like while choosing the numbers, so when we explore, so we prefer to choose the smaller number and then explore its neighbors. But we can choose another greater number also.
Yeah, you
But
can choose.
we
It's
prefer,
not a compulsory case.
but we prefer a smaller number.
But we prefer the smaller for a
Okay.
little bit simplification.
Okay, ma'am.
Okay. But you can choose any number you can choose.
Okay.
Okay, so now let's go to the directed graph. So we know what is a directed graph. Directed graph means where there exists one pair which has one-sided edge only. So for example, in this graph, here you observe that we have an edge from 0 to 1. So this is 1. So we have an edge from 0 to 1. We don't have an edge from 1 to 0. So that means this is a one type of pair of vertices where we just have one-sided edges. So such kind of graph is known to be a directed graph. So directed graph means we have a significance of direction. We have to maintain the directions too. We cannot just go into one direction and then come back. It is possible that there is no path for coming. Okay, such kind of graph is known to be a directed graph. So in directed graph, there are directed cycles. So what are directed cycles? So directed cycles are again only cycles, but here also we have to take care of directions. So for example, if I give you one cycle, so suppose this is right. So here we cannot say that this is a cycle, because we can move from vertex number 0 to vertex number 1, but we cannot go in this direction. So again, we can go to vertex number 0 to 2, but we cannot go in this direction. So this is not a directed cycle. Whereas if you observe this cycle, then this is a directed cycle. Okay, so this is a directed cycle. So for example, in this graph, this is not a cycle, because we can go to 0 to 1, but we cannot go to 1 to 5, right? We can go to 0 to 5, 5 to 1, but again, we cannot come back to 0 from 1. So this is not a cycle, whereas this is a cycle. We can go from 0 to 2, 2 to 3, and 3 to 0. So such kind of thing is known to be a directed cycle. So DFS tree, a DFS process will help us to identify cycles in a directed graph. Now, if you have undirected graph, so if you have undirected graph, so in undirected graph, there is a result. That result says that whatever edges, or those edges which haven't used in the BFS or DFS process, so those edges which haven't used in DFS or BFS process will create a cycle. It's a very obvious result, because what happened if we have an undirected graph, then we can extract one tree from BFS and DFS process, right? And if we are looking at those edges which are not used in BFS and DFS process, so that means these edges are not present in a tree. So if we append these edges into our tree, then obviously it will create a cycle, because we know what is a tree. Tree is a minimally connected graph. So if you add one edge, it will create a cycle, and if you remove one edge, it will disconnect the graph. So what we are doing, so these edges, if you add these edges into your BFS and DFS tree, they will create a cycle. So if they are creating a cycle in a tree, then obviously they will create a cycle in our original graph too. So this is the one remark, that in undirected graph, whatever edges we haven't used, if you see all those edges, then all those edges will form a cycle. So these are the edges which are creating a cycle in our undirected graph. But this is not the case in directed graph. Okay, so we'll understand that by using DFS numbering. So first understand what is a DFS number. Is this case is clear of undirected graph? That means if we have undirected graph, and if we append those edges in our tree, which are not used in BFS or DFS process, then those edges will create a cycle. But this is not the case in a directed graph. And why is this so? We will see here. But before that, let's know what are the DFS numbering. Okay, so what is a DFS? DFS numbering means we are giving two numbers to every vertex. One is a pre-number, another one is a post-number. So we are giving pre-number and post-number. So when we'll give a pre-number, so we'll give a pre-number to a vertex when we reach to that vertex at the first place, right? So that means if I reach to vertex number 1 in the first place, in the count number 1, then I'll give you the pre-number 1 to the vertex number. So that means we will give pre-number to vertices if we reach to that vertex. And when we'll give a vertex to be a post number, so if we backtrack from that vertex, or if there is no new information we can get from that particular vertex, then we will add a post number, or we will attach one post number to that particular vertex. Okay. And again, these pre-numbers and post numbers are counters. So counter means we are counting something. So if the first pre-number is 0, the next pre-number will be 1, next pre-number will be 2. And after this 2, if we want to give a post number, then that post number will be 3. Because here we don't have to break our count. So we will give pre-number, post number using only one count. One count means 0, 1, 2, 3, 4, 5, 6, until and unless we have finished the whole DFS process. Okay. So let's understand what are these pre and post number using this particular graph. Okay. So initially we start our DFS process from vertex number 0. So since we are starting, we'll give pre-number 0 to the vertex number 0. Then after that, from vertex number 0, we can go to vertex number 1, 5 and 2. So we'll go to vertex number 1 again just by our convention. So since we are reaching to vertex number 1, we'll give the pre number 1 to vertex number 1. Okay, so we will give pre number 1 to vertex number 1. Now from 1 also I have choices to go. So that means from 1 I can go to vertex number 4. So now I'm entering in vertex number 4. That's why I'll give vertex number 4 the pre number 2. Okay, so we will reach at vertex number 4. So I'll give you vertex number 4 to pre number 2. Now again from 4 we have 3 neighbors. We can go to 5, we can go to 7, we can go to 6. Again by our convention we will go to 5. And since we are entering into 5, we'll give it a pre number 3. So we will enter 5 with pre number 3. Now from 5, I have one choice, which is vertex number 7. So that means we will go to vertex number 7 with pre number 4. So since we are entering in vertex number 7, we'll give one pre number, and that pre number will be 4. Why it will be 4? Because the previous pre number is 3. And pre and post number are counters, so that's it. Now from 7, we don't have any new information, or we cannot go to any unvisited vertex from vertex number 7. So that means from vertex number 7, we have to backtrack, or we have to leave vertex number 7 in our DFS process. So as we leave, or as we backtrack, or as we don't have anything new from that vertex, we will assign it a post number. But again, since pre number and post numbers are counters, they will given in a certain order. Order means 0, 1, 2, 3, and now the post number will be 5. So now we will attach 5 post number to vertex number 7 and go to vertex number 5. But again, from vertex number 5, we cannot go to anything new, because from vertex number 5, we can go to vertex number 1, but the vertex number 1 is already visited. So that's why at 5 also, we have to end our DFS process and leave this vertex. And whenever we are leaving a vertex, we will attach a post number to this vertex. So now we will attach a post number 6, because again, pre number, post numbers are counters. So you have to maintain the sequence. So now we will attach a post number 6 to vertex number 5 and go to the vertex number 4. But again, from vertex number 4 too, we do have one choice, right? We can go to vertex number 6, because vertex number 4 have 3 neighbors, vertex number 5, 7, and 6. And 6 is unvisited. So that means at 4, we haven't finished our DFS process. So that's why we don't add any post number to vertex number 4 now, because we have a choice. So we can go to 6. So now we will enter 6. Now what is our count? So count is 6. So the next number will be 7. And what will be the next number? Next number will be pre number for vertex number 6. So we'll enter vertex number 6 with pre number 7. But again, from 6, we can only go to 7, but 7 has already been reached. So we have to finish our DFS process at vertex number 6. So now we have to backtrack, or we have to finish our DFS process at vertex number 6. So whenever such kind of scenario happen, we will attach a post number. So here the number is used so far is 7. So we will attach a post number 8 to vertex number 6 and backtrack to vertex number 4. Now again, vertex number 4 doesn't have anything new. Vertex number 4 has 3 neighbors only, 5, 7, and 6, and all of these neighbors are visited. So that means we don't have anything new information from vertex number 4. So that means we have to leave our DFS process from vertex number 4. So we will add a post number to vertex number 4 and go to vertex number 1. So now at vertex number 1 also, we don't have anything new. So we'll again add a post number 10 at vertex number 1 and leave it, and now go to 0. Now from 0, we have choices. From 0, we can go to vertex number 2. So that means on 0, now we won't attach a post number, because there are new choices from vertex number 0. So now from vertex number 0, we go to vertex number 2 with pre number 11. Why it is 11? Because the previous counter is 0. Sorry, previous counter is 10, right? So that means we have to maintain the sequence. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and now 11. So the pre number of vertex number 2 will be 11. Now from 2, we can go to vertex number 3. So now the pre number of vertex number 3 will be 12. And now at 3, we don't have any new choices. So that means from here, we have to backtrack or suspend.
Ma'am, from why you are getting the pre numbers?
Pre number when we are entering the vertex. If you enter a vertex, then you will attach a pre number.
Ma'am, but how can 11 be the pre number of 2?
Yeah, it can be, because we are at we have took 11 steps to reach the vertex number 2, right? So one step will be 0. At 0, we have 0. Why cannot it will be 11? Again, I'll say the pre number and post number are counters. So you have to maintain the sequence. So that means sequence when numbering should not break. So the last post number was 10. So another number you have to use, then that will be 11 only. Is that clear?
Hello, ma'am. Can you explain me the numbering of the 4 and 4? I mean, it shouldn't be 7.
मैम ये प्री
Numbering of
नंबर और
4.
पोस्ट नंबर क्लियर नहीं हो रहा है.
See. Okay, let's start. So pre-number क्या है? तो so the pre-number is a number we are assigning to a vertex when we are entering in that vertex, right? So when we are entering in that vertex, then we will assign a pre-number, and we will assign a post number when we exit that vertex, right? So when we exit that vertex, or we will finish our DFS process at that vertex, we will assign a pre-number. But one thing you have to keep in mind, you have to give a number in a sequence. So that means if the first number is 1, another number will be 0, another one number will be 2, and the next number will be 3, and so on. But here, this won't affect the pre and post numbering. So that means it is possible that the one pre number is 1, another post number will be 2, then another pre number will be 3, 4, 5. Right? So you don't have to break the sequence of numbers. Why? Because these are counters. They are counting something. So that's why you don't have to break the sequence of numbers. So again, as we will start our DFS numbering from 0. So the pre-number will be 0. Right? Now we are entering 1 and the previous pre-number is 0. So that's why the pre-number of 1 will be 1. Okay, pre-number of 4 will be 2. Because we are entering 4 with the pre number 2, because we are entering 4 now. So as we enter any vertex, we'll assign a pre number. And what will be the pre number? The previous whatever counter we have used so far plus 1. So the counter we have used is 1. So 1 plus 1 will be 2. Okay. Now
So
from
5 pre number.
will be 3.
Yeah, okay. And
Now what will be the 7th pre number?
4.
Right. Because we are entering 7 now. So as we enter, we have to assign some pre number. And
So
what will be that pre number?
how many ways we can enter a number? It's a pre number of the particular number.
No,
up to
that is not the thing. Pre
How
number,
many
post number are
steps we have
different.
taken to reach that number is
हाँ,
the pre-number, है
to
ना?
that vertex.
Yeah,
Something like this. Okay. Now from 7, we don't have anything new. So we have to end our DFS at 7. So whenever we end our DFS or whenever we are backtracking from that vertex, we have to assign a post number. So now we'll assign a post number. Now, but the post number will be 5. Why? Because again, pre number and post number are counters. So we don't have to break our count. So 0, 1, 2, 3, 4. And now the post number will be 5. Is that clear?
Yes, ma'am. Now clear.
Now, can we assign the post number to vertex number 5?
Yes, ma'am.
Yes, ma'am, it's 6.
Right, because there is nothing new from vertex number 5 also. So we have to end our DFS here and assign the, but from 1, we have new choice. So from vertex number 4, we can go to vertex number 6. That's why we now cannot assign the post number to vertex number 4. Because here we are not ending our DFS, we are extending it with the help of vertex number 4. Right? So that's why we don't assign the vertex number 4 any post number and go to vertex number 6. And now we are entering vertex number 6. So that's why we have to assign a pre number. So now what will be the pre number? So whatever number used so far plus 1. So 6 is used so far. So that means 6 plus 1. So the 7 will be the pre number of vertex number 6. Okay, is that clear now?
Yes, ma'am.
Okay, so now we will assign a post number to vertex number 6 because again there is nothing new. So the post number will be 8 because after 7 we have to attach one number. So after 7, 8 is there. So we will attach 8. Is that clear?
Can we
Yes,
take
ma'am.
after 4 number 2?
After 4, can we take 2?
Can we take 2?
No, because 2 is not connected to 4, right?
Ma'am, 6 is also not connected to 4, no?
6 is connected to 4. This is an edge.
It will be 3.
there is
6
a
is
question.
connected to 4 via this edge,
Okay, ma'am. Okay.
right?
Yeah.
So
There is
now,
a question.
yeah,
So, from 4 to you're going 5, and
yeah,
5
4 to
to
5,
7. Why
7,
not first 4
5 to
to
6,
7?
4 to 7. Yeah, you can go, but again, yeah, it's my choice, right? It depends on the choices. So you can go to 4 to 7 too. It's up to you. So if you go to 4 to 7, so suppose 4 is there. So the pre number of 4 is 2. So if you go to 7, then 7's pre number will be 3. But from 7 now you cannot go anywhere. So you have to assign a post number here. So now the post number will be 4. And now we'll go to vertex number 4. But from vertex number 4, we have choices. We can go to 5 and 6 then, if we are choosing 7. Okay. So now you can choose any vertex. That's also possible because here we are using DFS process, right? In DFS process, you have choices. You can go to any vertex.
Yeah.
But
So
then,
if you're
yeah, I
going
know
there,
that,
depth you have to go.
yeah, again, you have to go to 4. Back.
Okay. So whichever makes
Yeah.
us clear, I mean, shorter, then we have to choose that.
Yeah, it's up to
Because
you. Because whatever DFS tree or whatever numbering you will choose, the result will be same. So now we will see some relation between the edges and this numbering. That result won't affect if you choose any other way to imply your numbering. Okay, so that's the reason. It's up to you. You can choose any vertex. Okay. So let's move ahead. So now we will.
okay, ma'am. Thank you.
At 4, we'll assign a post number. 9, go to 1. Again, assign a post number, go to 0. But from 0, we have choices that we can go to 2, we can go to 3. Because there are edges, right? So you have to consider the edges and also the direction of edges. So you can go to 0 to 2 with the pre number 11. From 2 to 3 with pre number 12. But again, from 3, we don't have anything new. So we'll assign a post number 30. Go to 2, assign a post number 14. And go to 0 and assign a post number 50. So now this is the whole DFS numbering for this particular graph. Is that clear? Any doubt?
So only we can draw the tree. This is enough, right? Or else we have to numbering also. We have to do.
Means?
So any exams or any questions, the post number also important or?
Yeah, post number are also important. So now what happens? So there are.
Ma'am, I got
Yeah.
the point which you have told, that the pre-number concept I have got, because how many OS we are traveling to reach the particular number,
Yeah.
but how we are determining the post number?
See,
Because
post number will be the number where we are ending our DFS process. So that means at 10th step you will end here and then go to the next vertex. So the next vertex will
but
be
ma'am,
then 2. So we are entering 2.
5's pre-number is 3, because we from 0 to 1, 1 step, 1 to 4, second step, and 4 to 5, the third step is 3. But
Yeah.
after completing this process, how we are getting that the
See,
post number
post
of
number
5
will
is
tell
6?
us when we are ending our search at a particular vertex. So we are ending our search at particular vertex at 6 steps. So that means we go to 7. And then from 7, we explore that there is nothing to explore. So here 5 will tell us we are ending our DFS process at 7. And then after go to 5 and then end the DFS process at 6. So that means at 5, the DFS process end after ending at 7. So here, if you consider the interval, so the interval is 3, 6. So now using pre-number and post-number, we can form an interval. So this interval, so this is the interval for vertex number 5. And the interval for vertex number 7 is 4, 5. Now here, what is happening? The pre-number for 5 is 3, which is less than the pre-number of 7. So which will tell us that this 5 is actually been explored in DFS process before the vertex number 7. Okay, and here the post number is 5 and here the post number is 6. And since the post number is less, it will show us that vertex number 7 will get ended before vertex number 5. So that means in a tree, so if you draw a tree, so in a tree, vertex number 5 will be some kind of ancestor or a parent of vertex number 7. Right? So here the ancestor parent means, so suppose there is an edge from any vertex A to any vertex B, then this A will be a parent or ancestor of a vertex number B. So if here in this particular graph, the vertex number 5 is a parent of vertex number 7. So ultimately it's coming before vertex number 7 in our DFS tree. So this is the thing, these pre-number and post-number will tell us. Okay, so similarly,
we can say that the post
number
five
actually tell us when our
post number of
vertex get active.
five. Sorry, post number of 5. We can consider as 0 because the parent of 5 is 0.
No. Parent of 5 is not 0. The parent of 5 is 4. 4's parent is 1. 0 is the ancestor of 5, right? So parent, parents, grandparents, and then grandparent.
So
there are difference.
So ma'am, can you describe from the graph that how you are getting the 0.6 after 5 post?
See, post number, pre number are just counter. You just have to assign one number to a vertex. And how we are assigning, this is the process. As we enter your vertex, we'll assign a pre number. As we stop our BFS process at that particular vertex, we'll assign a post number. So these are just the numbering we are doing in a particular way. And now this way will lead us to a good significant result. And that result is, we can actually tell which are the edges, which are the edges forming a cycle. So pre-number, post-number is just a numbering and just a way or just a method to describe a way to number our vertices to get such kind of intervals, which will tell us that if the pre-number of 5 is 3, so that's why 5 will get explored first in our DFS process, sorry, and 7 will get explored after the vertex number 5, and 7 will end before the vertex number 5, and then 5 will end. So this is the thing this numbering is doing.
How the question will be asked in this? So they'll give the interval and asking vertex or what? Vertex given or
so
interval
they will
will be
ask
asked.
you about forward edges, back edges, and cross edges. So what are those edges? So let's see. So there are different type of non-tree edges. So non-tree edges means these edges in a graph which are not used in our DFS tree. So for example, this edge, if you consider 5 to 1, then this edge we haven't used this edge in our DFS tree. So this is a non-tree edge, and this edge is actually growing along the direction of tree. So what is the direction of tree? Direction of tree is downward. So this edge is growing along the direction of tree. So such kind of edges are known to be a forward edges. Similarly, we have back edges. So back edges are those non-tree edges which will grow opposite the direction of tree. So for example, these red ones. So this red one, 5 to 1. So this, initially I have taken, so this is our forward edge because it grows along the direction of tree, and the edge from 5 to 1, this red one, this is a back edge because it is growing out, opposite direction of our tree. So our tree is growing from 0 to 1 and then 1 to 5, but this edge is going from 5 to 1. So such kind of edges are known to be a back edges. Now there are different edges which grows along the branches of a tree. So these two are the branches and these are also branches. And so 6 and 7 are in the different branches of tree. So such kind of edge is known to be a cross edge. So there are 3 kind of edges, and the result says that forward edge and cross edges won't create a cycle. So here you observe that this 0 is a forward edge, this edge is a forward edge. And it is not creating a cycle. Why it won't create a cycle? Because for creating a cycle, we need some triangular kind of situation. So since our tree is growing in the downward direction, so if we have a forward edge, then that edge also grow in a downward direction. So here, using these direction, that all the edges pointing into one downward direction, we cannot form a cycle, right? So that's why forward edges won't create a cycle. And similarly, cross edges also won't create a cycle. Why? Because our tree is growing in a downward direction. So here, no matter which edge, if you add edge, append in this way, because it is a cross edge, right? It will grow from one branch of a tree to another branch of a tree. So if you append an edge in this way, then this is also won't create a cycle. And if you append any edge with the opposite direction too, it won't create a cycle. So that's why cross edges and forward edges cannot create a cycle, but back edges can create a cycle. Why is this so? Because we have 2 edges which are going in the downward direction, and we have one edge which is growing in the opposite direction of these two edges. So if we append this edge, yeah, we can understand here better. So here observe that this is a back edge from 5 to 1. So we can go to 1 to 4, we can go to 4 to 5, and then 5 to 1. So this back edge is actually creating a cycle. So this numbering will help us to tell us which edges are back edge, forward edge, and cross edge. Yes, there is some doubt.
Why is there a cross edge from 3 to 6? Is it because it's from a different branch?
Yeah, this is because they are from the different branches of tree.
So 6 is also another branch. Okay, yeah.
6 is also another branch.
So it's pointing to a different branch also. So it's a cross edge.
Yeah.
Okay.
Ma'am,
Yes.
can you explain the parent concept again?
Yeah, so this is not a general way to explain. See, parent mean, see, we are reaching vertex number 7 from vertex number 5. So we can say that 5 is a parent of vertex number 7 in DFST. In DFS process, we generally don't bother about parent because it can change very rapidly because we have so many choices. So if you have such kind of tree, then we can say that 5 is a parent of 7 because we can reach 7 using vertex number 5. Similarly, we can say 4 is a parent of 5 and 6 both. Okay, because we can reach vertex number 5 using vertex number 4, we can reach vertex number 6 using vertex number. Similarly, we can say 1 is a parent of 4, 0 is a parent of 1 and 2 both, and 2 is a parent of 3. So this is one way we can describe parents.
Ma'am, and can you also explain the cross edge again?
Yeah, we can explain the cross edges and all those edges using the parent information too. Because here you observe that what is happening in the forward edge. So in forward edge, there is a forward edge from vertex number 0 to 5, but let's take another forward edge. So there is a forward edge from vertex number 4 to 7. And 4 is some kind of ancestor of vertex number 7. So whenever we have a vertex, which is an ancestor, ancestor of another vertex W, and if there is an edge from V to W, then that edge is known to be a forward edge. But this is another kind of description which we haven't taught in video, so that's why. So if there is an edge from ancestor to any other vertex, so suppose V is an ancestor of W, and there is a non-tree edge, right? They will be a non-tree edges. These are not edges which we are used in tree. They all are non-tree edges. So if there is a non-tree edge from any ancestor to any other vertex, then that will be a forward edge. And if you take the backward thing, so that means if there is any edge from the vertex W to its ancestor, then that will be your back edge.
So ma'am, the like as a 4 is also ancestor of 0.
No. 0 is the ancestor of 4. Not 4 is the ancestor.
Oh yeah,
of
okay.
0.
Yeah, okay,
Yeah.
got it.
Is 1
And the
1
back.
to 4 forward edge. 1
Yes,
to 4
Aditi, what?
forward edge. 1 to 4 is it a forward edge?
No. 1 to 4 edge we have used in tree. So we are talking about non-tree edges, which are not used in our tree. So we don't categorize tree edges. So whatever edges are used in tree, we don't name them. We just name all those edges in our graph which haven't used in a DFS tree. Okay, so 1 to 4 edge is used in our tree. So we cannot say that this is a forward edge or back. Okay, so in backward edge, you observe that 1 is the ancestor of 5, and there is an edge from 5 to 1. So such kind of edges are known to be a backward edge. And what are the cross edges? So cross edges means if the parents are different. So for example, the parent of 6 is vertex number 4 and the parent of 7 is vertex number 5, different parents. So that's why this edge will be a cross edge. Similarly, the parent of 3 is vertex number 2, the parent of 6 is vertex number 4. That's why the edge from 3 to 6 is a cross edge. So this is another way for describing forward edge, backward edge, and cross edge using the parent. Is that fine?
Ma'am, can we draw a cross edge from 6 to 3? Or it will be only from 3 to 6?
Yeah, see, it will be only from 3 to 6 because in our original graph, there is an edge from 3 to 6. That's why we cannot draw backward. We have to use all those edges which are present in the graph only. If you observe that all these edges are already present in a graph, so that's why we are using.
Ma'am, can we tell 0 is the ancestor of 1 and 2 also?
Yeah, 0 is a parent of 1 and 2.
So parent and ancestor are different.
Parent and ancestor are different. Ancestor means parent's parent.
Okay, so 0 is the ancestor of 4, but 0 is the ancestor,
Yeah.
no, parent of 1 and 2.
Yeah, right.
Okay, and child will be 0 is 1 and 2 will be the child of 0.
Child, right.
Yes, okay, thank you.
Yes, Satya. Okay.
And this
Ma'am,
forward
three.
and backward will be on parents only, right?
Forward and backward will be on
I mean,
parents means?
forward edge and back edges are like within the parents and child only.
Within the ancestor and child. Yeah.
Ma'am, here
Within
3 is the
ancestor
grand.
and child, not child and parent.
Actually, there could be situations. So suppose we have such kind of edge, then this is also possible.
Ma'am, but
Okay,
So it is
so
possible,
the
child parent.
forward, okay, it is possible for a forward and backward edges in between parents and ancestor and childs.
Right.
Okay, got it. Thank you.
ma'am, but in the case of 3 is a grandchild of 0.
Yeah, but in case of cross edges, we just talk about parents only. We won't go to grandparent because obviously 0 is the 0 is the ancestor of every vertex. So then there will be no cross edge. You're getting my point. So that's why in cross edges, we just look for the parent. If the parents are different,
So
then we'll
what
see
is
the
the
cross
relation
edges.
between 7 and 6? What we can say?
See, 7's parent is 5 and 6 parent is 4. So both are different. So that's why this edge will be a cross edge.
And for in the forward edge, we are just comparing the particular element with its grand element.
Right, something like this you can say. But see, this description is little bit, I cannot say tough, but it's easy to understand in a direction of a tree, right? So if the edge is in direction of tree, then it will be a forward edge. If it is in opposite direction, then it will be a backward edge. And if the edges are among the branches of tree, then it will be a cross edge. I think it's better to understand this way too. Whatever way you guys will take.
Yeah, I'm now understand.
Okay. Now we can actually judge which non-tree edges are forward edge, backward edge, and cross edge using the DFS numbering. So here are the 3 rules. So what does the rule says? So if you have an edge from vertex number u to vertex number v. Okay, suppose I have an edge, I have a non-tree edge from vertex number u to vertex number v. And the pre and post number of vertex number u are in this way, that pre of u and then post of u. And then similarly pre of v and post of v. Okay, and here if this interval is contained in the interval of vertex number u, then this edge is known to be a forward edge. See, here is written already that if post of u comma pre of u comma post of u contains pre of v comma post of v, then this edge u to v will be a forward edge. And why is this so? Because see, pre of u is bigger than pre of v. So this will imply us that u will come before in a tree, before in our DFS tree. And since post of v is again less than post of u, this will also indicate the same thing. So ultimately what is happening, u is before in our DFS tree from v. And if there is an edge, if there is a non-tree edge from u to v, then this edge is actually growing in a direction of a tree. So that's why it will be a forward edge. Similarly, if the opposite thing happen, then that will be our backward edge. Okay, so if the opposite thing happen, opposite thing means
Ma'am,
there
could
is
you
an edge
repeat
from
once again?
Yeah, sure. See, if we have two vertices u and v and there is an edge between u and v, then that edge is known to be forward edge if this particular interval for u contains the interval of. And why is this so? So if this interval contains this interval, then pre-u is greater than pre-v. And if pre-u is greater than pre-v, it will give us a information that in DFS process, we are entering u before entering v. Right? And if post u is greater than post v, then it is showing that we are exiting u after exiting v. So for example, here you observe that if you contain the interval of vertex number 0, so that will be 0, 15. Or else you don't want to go to 0, let's go to 4. Okay. So what is the interval for vertex number 4? So for vertex number 4, the interval is 2, 9, right? 2 and 9. And what is the interval for vertex number 7? So the vertex number 7 has interval 4, 5, right? Now this 4, 5 interval contained in 2, 9 interval. And there is an edge from 4 to 5. Now this edge, which is from 4 to 7, then this edge will be a forward edge. Because again, so since pre number is 2, which is less than 4, it will tell us that we are entering 4 before entering to before going to 7. Right? We entered 4 before going to 7. And this post number is greater will tell us there we are exiting 4 after exiting 7. So that means we exit 7 at post number 5, and then we go to 5, then we go to vertex number 5 and exit it, and then we go to vertex number 4 and exit. So this containment shows us that 4 will lie before the vertex number 7. And if there is an edge, then that edge will follow the direction of our tree, and hence it will be a forward edge. Is that clear?
Ma'am,
Yes.
I mean, it's likely to contain, but it's not right for all the cases, right?
No, it is for forward edge, it is the case.
Ma'am, but like if you have taken 4 and 7, but what if we take 4 and 5?
Why do we want to take 4 and 5? There is no edge from 4 and 5.
Oh, okay, ma'am.
Right. Although if you take 4 and 5 and suppose there is a non-tree edge from 4 and 5, still it works, right? There is 2 and 9, and then there is 3 and 6.
Yes, still it
And
works.
3x
Yeah.
is contained in 2 and 9.
It is like a cycle, ma'am. So 2, 3, 6, 9. So it will be round off.
Right.
So correct. So it's a forward means we are coming from that direction and again we are going back direction. So obviously it is be ascending order to anti-clockwise.
Right. So if the opposite happens, so that means if there is an edge from V to U, and the containment is opposite. So containment opposite means something like this. So suppose there is an edge from U to V. So if there is an edge from U to V, and this vertices interval is containing, the pre-U, post-U contains the vertex number U. See, in the forward edge, what is happening? If we have an edge from U to V, then the interval of U should contain the interval of V. But in backward edge, the opposite happens. So that means if we have edge from U to V, then interval of V will contain now the interval of U. So for example, here, so we have a back edge from vertex number 5 to vertex number 1. So observe that. So we have an edge from vertex number 5 to vertex number 1. And what is the interval of vertex number 5? Is 3, 6. And the interval of vertex number 1 is 1, 10. So here 1 is working as V and 5 is working as Z. So that's why this interval of V contains interval of U. Because this 3, 6 is contained inside interval 1, 10. Correct? So if because opposite kind of scenario happens, then it simply shows that again the same logic. Since pre number is smaller, so it will be before the vertex number. Oh, sorry. Since the pre number 1 is here smaller, so it will be before the vertex number U in our graph. The same logic here for back.
Ma'am, it is the same logic of forward, right?
Same logic only.
Then how
same
do
logic
we
only.
define
See,
it
here
is
the
backward or forward?
direction changes. So in forward edge, we are dealing with such kind of direction. There is an edge from U to V. There is an also edge from U to V, but we are taking pre-V, post V. Here we are taking pre-U, post. Okay, containment will happen, but which contain which interval, that will tell us it will be a forward edge or a backward edge. Okay, let's see one example then. So let's take 0, 3. Okay. So there is an edge from 0 to 3, and the interval for 0 is 0, 15, and the interval for 3 is 12, 13. Right? So here what is happening? There is an edge from, not 0 to 3, there is an edge from 3 to 0. Okay, there is an edge from 3 to 0. So, and here what is happening?
No,
this
ma'am,
interval,
it's
0, 15.
0 to 3 only.
No, 3 to 0. Direction is opposite. No? 3 to 0.
Oh,
It's
sorry,
back edge you are trying to say.
I was
That's
seeing
what
pre-image
Oh.
of 5 and I was thinking something. Sorry.
right. So here, this vertices interval is containing this vertex interval. Whereas if we have a forward edge, so suppose I'll draw the edge in the same direction. So we have a forward edge from 0 to 5. So I'll have to draw 5 and then 0. Okay, so what are the interval of 0? So 0's interval is 0, 15 and the 5's interval is 3, 6. And here observe the containment is in this direction. So that's the thing. Okay. So in this way, we can judge what are the forward edges and backward edges. These are little confusing, but just sit and understand. Try to think that why this kind of scenarios happen. Okay, then it will be easy. Okay, is that fine? Okay, silence we have. Fine. Just sit and try to understand what are the things or what is this pre and post number is telling us. So if the pre number is smaller, it will tell us that that particular vertex is being explored before in our particular DFS process. Okay, this is the only logic we are applying it. Now for cross edges, if the interval are disjoint, then we are saying that they are cross edges. Because if the interval are disjoint, they will lie in a different branches. Because here you observe that any vertex which is lying in different branches, their interval is disjoint. So here one is lying in another branch, two is lying in another branch. So here the interval is 1 and 10, and here the interval is 11, 12. And why is this happening? Because if we want to go from one branch to another branch, we have to end all the post numbers here. And after ending post number, we have to start the pre number after the end of the post number. Right? So here post number is 10, here pre number is 11. So that's why this is a reason for disjointness. So whenever we have vertices sitting over the two different branches, then the intervals will be disjoint. And if there is an edge between these two vertices, that edge will be a cross edge. Okay. And only backward edges will create a cycle. So if we have such kind of containment, then we can say these are the backward edges and these are the edges which can create a cycle in our particular graph. Okay, is that fine?
Excuse me. Actually, I have a small doubt. Ma'am, these black colored edges are actually the tree edges which we made while doing the DSF process. So when we're looking for the forward, backward, and cross edges, we don't actually consider these tree edges. So we just add conditions which are given and then we mark them. So we don't take these black edges into consideration while we are
right.
Okay, ma'am. Yes, ma'am.
Because these are non-tree edges, which we are not using in our DFS process. Because these are the edges only which can create a cycle.
Okay, understood. Thank
you. Any other doubt?
Ma'am, like from I'm talking about back edges. From 3 to 0, we are having a back edge, right? So we are checking interval of 0, which is 0 to 15. And we are checking interval of 3, which is 12 to 13. So we are telling, because 0 is smaller than 12, so it's bigger, like it's coming before of 12. So there, the 3 is happening after 0, right?
After 0, right.
Yes, ma'am. That's why we are making a back edge over there.
Right.
In the case of this 5 to, oh, sorry, forward edge also, it's happening the same, right? We are
Same,
checking
but
if
the direction of edge here is different. We have 3 to 0, and now here we have 0 to 5. So the U and V will got replaced.
Ma'am, can without having the graph, by looking at the intervals, can we guess which is forward and which is backward?
Right, we can guess it. See, let's see. So suppose we have this interval. Okay, here you have to tell from which interval to which. You have to tell the direction of H2. Just by looking at the interval, we cannot guess. Yeah, so that's your question, right? Just by looking at the interval, can we guess?
Yes, ma'am. Yes, ma'am.
No, we need the direction of H2. So if it is an H from this interval to that interval, or is this, or it is an H from the reverse way down. So we need this direction too. So the forward and
Okay,
backward
so
edge is
compulsory
depend on
the
the
graph
direction.
is required.
The graph or the direction of an edge is required.
Okay, so it's like the same formula, but by seeing the direction, we are guessing it is backward or forward. That's it,
It's
right?
backward or forward, right?
Okay, okay, yeah, clear.
Fine. So that's all we have. All those strongly connected components is okay for this. Now let's go to the last topic, which is topological sorting. So what is a topological sorting? So suppose we want to do some work. So for example, if you want to make a good office space, then for that we need several type of we have to complete several type of tasks, and these tasks depend on each other. So for example, if you want to build a house, then first you have to go and lay the foundation, and in after the foundation you have to do the piping. So there are two type of piping. So all those things you have to do, and after that you will lay the tiles, and then do the plaster, then do the paint, and then do the wiring and all. I mean, we have to do the task in a certain kind of sequence. So every task is dependent on some other task. So this also happens when we choose the courses too. So for example, in our degree course, so we have maths 1, we have maths 2, we have maths 1, we have maths 2, we have stats 1, we have stats 2, right? And also we have Hindi, English. Suppose we have Hindi, we have English, and then we have the course ML. Okay. So now what is the requirement? So the requirement is that before completing, so for doing the ML course, you need to complete all these 6 courses. You have to complete here. So we don't have Hindi. So forgot about English. So for completing ML course, we need to complete these 4 courses. So that means Maths 1, Maths 2, Stats 1, Stats 2. But for completing Maths 1 course, I have dependency that for completing Maths 2 course, or for entering in Maths 2 course, we have to complete Maths 1 course, right? So that means this course, the completion of this course dependent on this particular task. So if you complete Maths 1, then only you can complete Maths 2. So this dependency we can denote it by an arrow, right? So again, we can form a graph using some dependencies. So here the Maths 2 course dependency is completion of Maths 1. So we can draw an arrow from Maths 1 to Maths 2. Similarly, we can draw an arrow from Stats 1 to Stats 2, right? Because the Stats 2 you can do only if you complete Stats 1 course. And similarly, for ML course, we have the 4 dependency. That means we have to complete Maths 1, we have to complete Stats 1, Maths 2, and Stats 2. But if you are completing Maths 2, that some sort of give us the idea that, okay, if Maths 2 is done, then obviously Maths 1 is already done. Because for starting Maths 2, you need Maths 1 course. So we can just draw an arrow from Maths 2 to ML course. That will tell us the dependency of ML course onto the Maths 1 course. And similarly, you have to complete the Stats 2 also. So if you complete Stats 2, then we can simply assume that Stats 1 is already completed. So we can draw an arrow. So this dependency we can formulate in a graph, and such kind of graph is known to be a directed acyclic graph. So any graph which will show us a different dependency, those are DAG means directed acyclic graph. Is there any doubt?
This is a transitive relation.
No, it is not a transitive relation. Yeah, fine. Transitive relation, correct.
Like, how could you give me the explanation of
See,
transitive
transitive
here,
means since S1 is related to no. See, here this thing is happening, but in general, it is not the case.
Ma'am, if my A comma B is there, B comma what is a transitive? So
See,
it should be
A comma B is there and B comma C is
B
there.
comma C is
Then
there,
B
then A comma C should be there.
Yeah.
Yeah, but here
So
I'm
A
not
comma C
relating
also
the
is.
S1 directly to ML. If this kind of edge is there, then you can say whatever relation represented by this graph, that will be a transitive relation. But now it is not transitive.
Okay. But however it is connected. So because we need the prerequisites of these 4 subject to continue ML, right?
Right. But see,
Okay.
we know that if match 2 is complete, then match 1 is already completed. So now ML does not depend on match 1 directly. It just depends on match 2. And then match 2 is depend on ML on match 1. So we don't need one edge from M1 to ML. We can just simply we can say the dependency of ML on match 1 course through using match 2 course. So that's why we don't need one explicit edge here.
Okay. But however indirectly we have to come from there. Okay.
Indirectly we need to come from there. So whenever we have such kind of tasks where we need to take care of some dependency, then those tasks we can formulate using a tag. Tag means directed acyclic graph. So directed means directed graph. Acyclic means there should not be a cycle. Why there should not be a cycle? So suppose you have a cycle. So suppose I have to complete 3 tasks A, B, and C. But I'm saying that task number A is depend on task number B is depend on task number A, task number C is depend on task number B, and task number task number A is depend on task number C. That means everything is depend on every other task. So for completion of A, I need a completion of C. For completing C, I need to complete B. But for completing B, I need to complete A. So in this way, I cannot start any task at any time. So if you have dependencies, then whatever graph you will form, that always be a tag. Tag means directed acyclic graph. Because in dependency, such kind of scenario cannot happen. Because if this is happening, then we cannot start, right? There is no starting point. So if there is no
Ma'am,
starting point, how we can
indirectly you're telling that for dependencies there is no cycles formed.
Right. So if you have dependency tasks, so whatever graph you will formulate, that graph will be automatically a DAG, directed acyclic graph. Okay.
So can we say there is no revisit of path, right? From if one from one it's starting, we should not come to one again in acyclic
we
graph.
should not come back to one acyclic graph.
Okay.
Now in directed acyclic graph now what we want to find out a sequence of vertices in which we can complete our task, right? So we want to find, so for example here if you make a sequence that okay, first I'll complete match 1, then I'll complete stats 1, then I'll complete match 2, then I'll complete stats 2, and then I'll complete M. So if you draw a sequence, so in this sequence you can complete every course. You can complete these 5 courses. This is a one type of sequence, but you can say that okay, no, first I'll complete all the maths courses, maths 1 and maths 2, then I'll complete all the stats courses, stats 1 and stats 2, then I'll go to M. So this is also some sort of feasible sequence to completing all these courses, right? So now we want to find out such kind of sequence using the graph. So for example, we have a DAG, then how we will find out such kind of sequence which will respect our dependencies. So now this sequence, so here whatever sequence we are getting, this sequence, these two sequences are known to be topological sorting. So you have to some kind of topological sort your graph. So topological sorting means you have to find out a sequence of vertices follow in such a way that if you follow that sequence, you can easily complete your task. Okay. That's the meaning of topological sorting. Now, there is a very fixed strategy for finding out topological sort in any directed acyclic graph. I'll just jump to that strategy. So it says that first, okay, so the strategy is, so the first thing is we have to compute in degree for every vertices. Right. So you have to compute in degree of every vertex. So what is the in degree? In degree means number of incoming edges. So if there are edges which are coming at that particular vertex, we have to count that number of edges. Those number of edges are known to be in degree. Okay. So for example, here, if you compute the in degree of every vertex, then what will be the in degree of 0?
0.
0. Because there are no incoming edges. What will be the in degree of 2?
2.
2, because we have 2 incoming edges. In degree of 5?
2.
2.
In degree of 6 will be 1.
1.
In degree of
1.
7 will be
3.
4.
7, 7, 4.
4.
In degree of 3 will be
1.
1.
1.
4 1
0.
0.
0.
Right. So this is the first step for topological sorting. Now there is a result which says that in directed acyclic graph, you will always find a vertex with integrity 0. So that means you will always find a vertex which has integrity 0. And why is this possible? So suppose we don't have this is the thing. Yeah, we will come to that. So the fact is that in directed acyclic graph, there always exists an vertex of integrity 0. Okay, and why is this so? So suppose assume that there is no vertex of integrity 0. So if there is no vertex of integrity 0, then I'll take one vertex named to be Vi. So now this vertex this vertex does not have a integrity 0. So that means there will be one incoming edge to this vertex. Correct? So now this vertex, if this is an incoming edge, it should start at some vertex, right? So it will start at some another vertex Vi minus 1. But again, Vi minus 1 does not have integrity 0 because we want to prove this fact using contradiction. So we are contradicting that, okay, we have a graph in which none of the vertex has integrity 0. So that means every vertex has integrity at least 1. So if the integrity of Vi minus 1 is 1, then again we can go back. There always a one vertex here. So again we will go back. In this way, if you go back, you will reach at a point where all the vertices has been used in this particular path. So we have to repeat one vertex here, right? So here we have to repeat one vertex. And as we repeat, we will create a cycle. So which will contradict our fact that this is a directed acyclic graph. So we are creating a cycle. So that's why in every directed acyclic graph, there will be a vertex with integrity 0. Is this fact clear? We're just going in backward direction. And since there are finitely many vertex, we have to repeat one vertex if you want to go backward more and more, right? So it seems like suppose you have at your home and you will just move one step back every time, and you want to say that, okay, I can and the case is that you can always take a step back. Then if you do that, then at the end you will create a cycle, because again, if there are finitely many areas, then we cannot take so many steps back. We have to go around a cycle too. You're getting the point? What is the proof here?
Yes, ma'am. If we go back, it will become a cycle. Then it's not acyclic.
Acyclic, correct. So now topological sorting. In topological sorting's first step is finding out a vertex of integrity 0. So now first we will list out all the integrity of vertices. Then find a vertex with integrity 0. Okay. So you'll find a vertex with integrity 0. But see here in our graph, we have two choices. So again, you can choose any one of them. But our convention says choose the smallest number. So you'll choose 0. But again, you can choose any one. It depends on you. So that's also here we have choices. As we have choices in our courses that you can complete Maths 1, Stats 1, Maths 2, Stats 2, and then ML. Or else you can say that I'll complete math courses first. That means Maths 1, Maths 2, then Stats 1, Stats 2, and then do ML. So there are two sequences possible, which says that a topological sorting need not to be unique. So we can have more than one sequences by which following on those sequences, we can complete our task. So here the topological sorting is also not unique. You will have different kind of topological sorting. It depends on a person's choice. Okay. So now this second step is find the vertex with degree 0. Now the third step says that list this vertex in your sequence. List this vertex in your sequence and remove it from your graph. So this is the third step. So we have to list this vertex in our sequence and remove it from our graph. So if we are removing the vertex, we also have to remove the edges associated to that particular vertex. And now update the integers. So now if we remove a vertex, we are removing some edges. So as we are removing some edges, it is possible that the integer will change for some vertices. And then repeat the same process again and again until and unless we cover all the vertices. So that means until and unless we will get our topological sorting. Until and unless we will get our whatever the number or vertices are there, that many number we should have in our sequence. Okay, so this is the steps. Now let's try these steps into our example.
Can you repeat from step number 3?
Yeah. So in step number 3, what we have to do, we have to select one vertex which has in degree 0 and remove that vertex from our graph and list that vertex into our sequence. So for example, here I am managing one sequence. So I'll list 0 first. Okay, because in our graph we have two vertices with in degree 0. So I'll choose 0 and list that 0 first and remove 0 from my directed acyclic graph. But as we remove 0, we also have to remove the edges. So as we remove edges from our graph, there will be some vertices whose degree will change. So now here, if I remove this edge, so you observe that the degree of 2 will change from 2 to 1 because there is only one incoming edge after removing 0 and after removing the edges of 0. Similarly, the degree of 3 will change from 1 to 0 because there is no incoming edge now. Similarly, the degree of 4 will change from 1 to 0 because there are no incoming edges. And we have to again after updating the degrees, we won't after updating the degrees, we'll just do the first step which says that compute the degree of every vertex because now they might changes, right? Since the degree of 2 will change from 0 to 1. So some changes will happen. That's why we have to recalculate the degrees of every vertex after removing the 0 vertex. Okay.
We'll
And
have
then
to
do the same
continue
process again.
after from 0, we have to continue to 2 or 3. Because the
From
degree of
0,
3 is 0.
Degree of 3 is 0. So we have to take either 3, 4 or 1 because now we have 3 choices. We have 3 vertices with degree 0. After
Okay,
deleting
so we
0.
can take any of them.
We
Okay,
can take
okay,
any of
thank
them.
you. Yeah.
Okay. So let's start. So yeah, so now this is the topological
Ma'am,
sorting. Yeah.
if we do such strategy, sometimes we might end up removing, like if we go from 0 to, if we list up 0, then we'll make 3 to 1 degree to 0 degree and 4 to 1 degree to 0 degree and 2 to
Right.
2 degrees to 1 degree.
1
Then
degree.
if we are not choosing next step is into 1, like if we are choosing like 3 or 4, then we might
Yeah.
be losing 2, right? Because after that, if it
No, no,
changes,
no.
then we might, yeah, please.
No, actually that won't happen because see what is happening here. So we are talking about dependency. So here vertex number 2 is only depend on vertex number 0 and vertex number 1. So as long as you haven't list your vertex number 0 and vertex number 1 in your sequence, you cannot list the vertex number 2. So you are saying that after choosing vertex 0, if we choose vertex 3, because 3 only depend on 0 and 0 is already been listed. So now we can choose 3, we can choose 4 and we can choose 1. So it's not the case that we are leaving 2 or this will create a problem. It's not the thing.
Okay, we are not updating 1, right? Yeah, understood.
Right.
Yeah, understood. Thank you.
Any other doubt?
No, ma'am, no. Please continue.
Sequence number can be changed, right? So 0, 3,
sequence
4
can
or 0, 1, 4, whatever, but it should be first 0 I have to take and next I have to take
Yeah,
the
0 or
removing.
1. 0 or 1. There also we have two choices.
What kind of question will be asking this?
In this way, obviously, they cannot ask you to find a topological sorting. They will give you 2 to 3 sequences, and you have to judge that which of the following sequence can be a topological sorting. Right? So they will give a sequence, and they'll ask that is this a topological sorting related to a particular graph or not?
Okay.
And how will
So
we
if
know
there
if it's
is
a
any,
topological sort?
You just have to compute and look at the choices. So here in the first place, you have choices 0 and 1. So if any topological sorting of this graph will either start with 0 or start with 1. It cannot start with 2, 3 or any other vertex.
Okay, so if
at
the
every
0
step, you
or
have to...
if the degree 0, we know it's a topological sort.
Yeah.
Okay.
So it should start from 0 or 1. So you have to consider choices at every steps. And then, or else you can see the dependency. So for example, here the vertex number 7, if you observe, that vertex number 7 is dependent on vertex number 3, 6, 4, and 1. So that means if 7 is listed before any of the 4 vertices, that won't be a topological sort. because we cannot go to vertex number 7 or we cannot complete vertex number 7's task before completing these 4 tasks. Correct? So if in a sequence 7 is listed before 3, 4, 6 or 1, then this cannot be your topological sorting. Because what we are saying, topological sorting is a way to complete our whole task. Okay.
Okay,
this
so
is
if the
another
in
way
degree
to-
is 0, we know it's a topological sort.
Means
In degree, you told in degree, for in degree of 0, it's 0, right? Because there's no edges. So can we tell
so
it's a
in degree of 0,
topological sort?
right. So
Because of
if a
that reason?
sequence, no, but this is the starting point. I'm saying that if a sequence start from 0 and 1, it can be a topological sort. It's not necessary that it will be a, but it can be a, it's a possibility.
0 and 1 here are the in degrees, right?
0 and 1 are the vertices whose in degree is 0.
But till last vertices,
Can you
we
give
have to
another
find this
example?
0.
Right.
Otherwise, it
Can
is
you
not. It's somewhere you will get stuck, means it will not topological.
Yes, Malvika, what's your doubt then?
Can you give another example for a topological sort?
Yeah, sure. So for example, I have, so it's actually it's little difficult to compute a graph, a DAG. So I'll just take a tree. So suppose this is your graph. Now here you have to choose a vertex with in degree 0. So here 1 is the only vertex with in degree 0. So your topological sorting must start with vertex number 1. Okay. At the first place, you should have 1. If you have,
Yes,
if they have given some options, so suppose there are options which start with 2, 3, 4, then obviously these options are incorrect.
Okay, thank you. Oh, okay, thank you.
And they'll ask such questions like from where it will start. Is it the
Yeah, it can be a question that from where your topological sorting can start.
ma'am, if we are starting from 1, then we'll go to the next step would be 0 or 7, right?
0, 2 or 7.
Or
Because if you remove 1, these 2 will have in degree 0 and 2 also has in degree 0. So you can list 0, 7 or 2, anything.
ma'am, can we say from by ordering we are by looking at the order at the end, can we say it is the increasing order of in degrees? Can we say like that? Like from here
Yeah,
we
can
are
say,
adding 1 into the
we
list.
can say actually.
Next we'll add 0, 7 or 2. From there we'll add 4, 3 and there 5, 6.
We can
Can
say
we say
because
like that?
Because if some vertices in degree is bigger, then obviously it depends on many vertices. Right? So here 7 vertex is in degree is 4. It is actually depending on 4 vertices. So after listing these 4 vertices only, we can list the vertex number 7 in our sequence. Okay, so let's complete our process. So start with the vertex number 0. Okay, so these are the in degrees. Now we have to start from some point. So start with 0. We started with 1. Okay, they started with 1. So also you can start with any of the things. You can start with 0, 2, you can start with 1, 2. So let's start with 1. So if you start with 1, you have to remove 1 and all the edges associated to it. So now removing the 1 and all the edges associated to it. Now the next step will be update the in degree of every vertex. Now here the in degree of 2 will change from 2 to 1 and in degree of 4 will stay as it is because there is one edge. So 3, okay, so all in degrees will stay as it is, only in degree of 2 will change. So now you have to choose a vertex with in degree 0 and that will be 0 now. Right, so update in degrees. So we can find a vertex with in degree 0, that was 0 and remove 0 and again update the in degrees. Now here we update, so the in degree of 2 will go to 0 now, in degree of 3 will go to 0 and in degree of 4 will become 0.
Ma'am, why didn't we update the in degree of 3 and 4? Because the edges were removed, right?
Yeah, but not the edges. I mean, there are no edges from vertex number 1 to vertex number 3. And
oh, 1 to 3.
that's
Okay,
what.
okay. Yeah, okay.
So they started with 1. That's so now here the in degree will update it to 0. So now we have 3 choices. You can choose 2, 3, or 4, anything. So let's choose 3. So if you choose 3, again we'll remove 3 from our tag and update the in degree. Now the in degree of 5 and 7 will get updated. So it will become 1 and 2. So in degree of 5 will become 1, in degree of 7 will become 2. Again, we have two choices. We can choose vertex number 2 or vertex number 4. So if you choose vertex number 2, remove the edge, the in degree of 5 will become 0. So in degree of 5 will become 0. Now again, we have two choices. Vertex number 5 we can choose, vertex number 4 also we can choose. If we choose vertex number 5, we have to remove it from that, update the in degree of 6 will become 0. Again, we have two choices, 4 and 6. You can choose any one. Let's choose 6. Then we have to remove the edge. So now the in degree of 7 will become 1 only. And at the end, we will remove 4. And at vertex number 7, in degree will become 0. And list the 7. So that's why I told you, see, 7's in degree is 4. And it coming at the last of the sequence. Because what is happening, 7 is dependent on 5, 6, 4, and 3. Right? But 5, 6 is dependent on 2. And 2 is dependent on 1 and 0. So that's why 7 come at the last of the topological sort. So in this way also you can discard some of the options if they have given you some topological sorters. So just find out the vertex which has a very large in degree and see somehow if the sequence contains that vertex at the starting, then it might be possible that that particular option won't be a topological sorter. Okay.
Ma'am, previously I've said that from going to left to right, the number of in degrees increase, right? Which
Right.
but now only
Here,
can I say that can I say only the starting and the ending element will have like various because in between 2,
right.
3 and 4 we have choice. We can choose any one of them. Like we can't say 100% that they have the least and the highest. So can I say only at the first and last there is 100% there is difference between
Yeah, obviously, because
in
the first one
degrees.
always be of in degree 0 and last one will always be of in degree some positive. So from first and
Yes,
last,
yeah.
yes, we can say, but yeah, in between we cannot say.
We can't comment on that. It will be a probability game.
So this is the topological sorter. Okay, so is there any doubt in the method how to find out the topological sort? Okay. So now if you guys have any doubts, we can solve some of the questions.
Ma'am, is week 10 completed?
Yes, week 10 is about all up to topological sort.
Okay. Ma'am, could you solve the question which I've sent you in the chat box?
Yes. Is my screen visible?
Yes, ma'am.
Okay, so this is your question, right?
Yes, ma'am.
Oh, this is, it's not graph theory question, right? But you have some kind of disturbance.
This is from mock quiz, ma'am. Of like if you're solving only week 10 questions, please don't solve.
Yeah, because actually it is a little calculative question. I think so. I haven't seen this question actually.
Actually, even I'm not able to calculate from there. Yeah. Okay, no problem.
Yeah, ma'am,
Yeah, I'll
this
let
is
you
from
know.
mock 2.
Yeah, I'll let you know the solution of this question. Okay, either I'll tell to you or I'll do it in the next session. Okay, so let's take from the week 2. So is there any doubt from week 10 activity? Sorry, practice assignment activity? Any question? I think in today's TS session, you guys have gone through some of the questions. So if you guys have any doubts, so then we can discuss.
Ma'am, is week 9 graded assignment and practice assignment session has been done?
Yeah, week 9 graded assignment and practice assignment session has been done.
Okay, ma'am. Is week 9 graded assignment and practice assignment session has been done?
Yeah, week 9 graded assignment and practice assignment session has been done. Graded SM practice TA sessions?
Yes.
Yeah, I think so. They are done.
Okay.
Will you
Any doubt
conduct
from
this
week
solve
10?
with the session of week 10?
Sorry, what? Of week
Solve
10,
with the
solve with
session.
a session.
Will you conduct? Is it possible?
Solve with a session. Actually, I don't have any update about that, but we can have solve with the session for week 10. I'll let you know because they haven't updated anything.
Yeah, okay.
So you guys don't have
Ma'am, if
any
no
doubt?
one, could you solve that if no one has any doubt?
Yeah, then we can solve it. So here Nisha reaches on various cosmic signals. So she found that a harmful cosmic y is equals to 3 to the power px has the potential to form the entire life form on the planet Earth. For her interest, she found two cosmic signals which are the point of x is this, g of x is this, where is greater than 0 and not equal to. Okay, so which can destroy this harmful stars. So she found that when a harmful cosmic signal passes through the intersection point of fx and gx, its effect nullifies before reaching the earth. So she has found the value of A so that she can, she has to find the value of A so that she can prevent the harmful cosmic signal from reaching the earth based on this information. So the following statement are correct. The equation fx is equals to gx has only one real root. Okay. Let's see what is fx is equals to gx. So fx is log base 2x plus 3 of 6x square plus 23x plus 21. And this is equal to minus of log base of 3x plus 7 of 4x square plus 12x plus 9. So here, if we what we can do, we can take log here,
Make
so it will become.
we can factorize
Yes. So,
the inside part. Yes.
does that simplifies the expression? Oh, what one
Yes,
thing we
ma'am.
can
Like
do now? Yeah, we'll factor it out obviously. So first I'll take this log over the left hand side and it will become plus of log. Then we'll apply the property that log m plus log n will be log n. So it will become 6x square plus 23x plus 21 multiplied by 4x square plus 12x plus 9.
Base
Oh,
are
this is
different.
4.
ma'am, bases are different, right? Ma'am, we can't do that.
Oh, yes. That's also.
But we can. What I've done is I have got the log part this side, like to the left side. I have factorized the value part 6x square plus 23x plus 21 and 4x square. I'm getting in terms of bases like 6x square plus 23x has as a root of
Okay,
2x
then
plus
it
3
will
and
become 1 and something will happen, I guess.
yes,
Okay,
ma'am.
so
Yeah,
what?
that.
So what are the roots are here? So
I'm telling 1 minute, ma'am. I'm solving. Yes, ma'am. For 6x square plus 23x plus 21, 2x plus 3 is one root and 3x plus 7 is another root.
And for this one,
For the right side one, only 1 minute. Get me a minute. It's equal roots. 2x plus 3, it has the equal roots. Yes.
2x plus
Yeah,
3.
that's the equation.
So
Yes, ma'am.
here this can be simplified because it will become 2x plus 3 and then plus of log base of 2x plus 3 of 3x plus 7. This is equal to minus of log base of 3x plus 7 and then 2x plus 3 to 1 square plus 1. Okay, so now this will become 1 and this thing will stay as it is. But here we have something, right? So we know that that this property, that log base a of x is actually equal to log base b of x and then log base b of x. So you can apply this property. So then log base is this 3x plus 7 of 2x plus 3 the whole square. So this we can write as 2 times of log of 2x plus 3. That means this is we have. So this will be equal to that log base of 2x plus 3 into, in terms of x, we have 2x plus 3 only. When I am treating this as our b, and this is our x, and I want to change it, sorry, this is our a, this is our x, and I want to change it into 2x plus 3 base. Okay, so it will become log of 2x plus 3, and here we have 3x plus 7. Okay, so now it will become just 1 upon log of 2x plus 3 of 3x plus 7. So that means ultimately we have 1 plus log base of 2x plus 3, 3x plus 7. This is our left hand side originally, right? Left hand side. And here we have minus of 2, 1 upon log of 2x plus 3 and 3x plus 7. And then plus 4.
Ma'am, can we reverse this? Oh, no, we can't do that.
Yeah, we can do it, right? So now we can take the LCM. That is one possible way. Yeah, so if we take the LCM, this will go here. It will become log of 2x plus 3 and then 3x plus 7 plus this term, this will multiplied by here. So it will become x square, right? That means log of 2x plus 3 into 3x plus 7, the whole square is equals to minus 2 plus 4 times log of whatever things we have. Correct?
How is it becoming a whole square? Could you just?
Because this expression and this term is same, right? So if I multiply the whole equation by this term, then it will become here log base 2x plus 3 into 3x plus 7.
Okay, you're multiplying that one. Okay, yeah, now understood. Yeah.
Now we can use our converting into polynomial method, right? So you can consider this to be equal to t. So equation will become t square plus t is equals to minus 2 plus 4 times t. Right? So this is same as t square minus 3t plus 2 is equals to 0. So this is same as t minus 1 and t minus 2 is equals to 0. Right? Because addition will become minus 3, multiplication will become 2. Is that fine? So t is equals to 1 or t is equals to 2. So that means we have that log base 2x plus 3 into 3x plus 7. This is either equal to 1 or log of 2x plus 3, 3x plus 7. This is 2. So from this, we can say that we know that log base ax is equals to y will imply a to the power y is equals to x. That means 2x plus 3 is equals to 3x plus 7. Correct? A to the power 2x plus 3 to the power 1 is equals to this quantity. So it will become x is equals to minus 1. Right? So 2x I'll take here. It will become 3x minus 2x will be x. And 7 I'll take here. So minus 7 plus 3 will become 4. So either x is equals to minus 4, or from here we have 2x plus 3 the whole square is equals to 3x plus 7. And this is equals to 4x square plus 12x plus 9 is equals to 3x plus 7, which is equal to 4x square minus 9x plus 2 is equals to 0. So this will become 4x square minus 8x minus x plus 2 is equals to 0.
Ma'am, not minus 9x plus 9x.
Plus 9x plus 3x. So here also we have plus. So 8 plus 1 will be 9. Multiplication will be 8. So 4x will take common, x plus 2. Here also plus 1 will take common, x plus 2 is equals to 0. So that means x is equals to minus 2. X is equals to minus 1 by 4. So these are the 4 roots we have. Now, I guess here we have one more restriction. So the restriction is this restriction that 3x plus 7 is strictly greater than 0. and 3x plus 7 is not equal to 1. So I think these restrictions will help us to either for discarding one of the solution maybe. So what we have, we want 3x plus 7 is either strictly greater than 0 and 3x plus 7 not equals to 1. So if I take x is equals to 7, x is equals to, if you take anything.
Yes, ma'am. From here I can do. I understood, ma'am. We'll only get one root, which is satisfying that condition. Understood.
Right. Any other doubt?
10.2 second and third question.
Hello.
Yes, ma'am. 10.2, the activity.
Yeah. Something else. Second and third question. Second question is, let games are presented as raw. This one, right? So let games are presented as nodes and there are edges between two nodes. If there is a clash in timing of the corresponding names, then choose the correct option which represent the best of the information. Okay. So here what you have to do, you just have to make a graph using this information. So every game will denote a node. So suppose just draw a node, and if there is a clash in timing, then you will you have to draw an edge, correct? So here for every game, they all start with the distinct letters. So I'll name the letters, name the vertices just by the letters. So F, D, R. But here is another one, so it's named to be T, E, and then battlefield, and then Titanfall. One is there, right? One more is there. So it's going to be H. Now, if there is a clash in timing, then we have to draw an edge between them. So here, this game starts from 10 to 11, and this game starts from 10:30 to 11:30. So there is a clash. So we will draw an edge between them. So we will draw an edge between them. Okay, so now the next game will start from 10:40 to 11:40. So this game clashes with these two. So we have to draw an edge in between them. So this game will clash with this game also, the first one also, and the second one also. Okay, now the third game starts from 11:30 to 12:15. So it won't clashes with the game do TA. So that means this game won't be connected to the, it's connected to the vertex number D, and it also won't connect to the vertex number vertex name F, but it will connect to vertex of R. So that means this will connected here. So this is the way. So now the battlefield starts from 11:50. So 11:15 it will cross this time slot. It only clashes with this particular game. So that means that here we have an edge. Now Titanfall starts from 12:30 to 11:30. So it will clash with battlefield, and it won't clash with any other of the time. And the last one starts from 12:20 to 1. Right? So 12:20 will clash with this game and this game. So we have an edge, Titan, and edge. Okay, so I have drawn something else. The graph is showing something else. So we have two type of cycles. If you observe, then here is the edge game, and it is connected to the two games T and B. They are connected with each other. And then B game is connected to the game D. Then that game is connected to the another game R. And then we have a triangle. Right? And this way, this will be an answer. Is that okay?
Okay. Yeah. So the next question.
Yeah. So the next question says, Find the minimum possible number of computers for the 2 months. So see, this is related to coloring. So if you say the minimum number of computers you need, right? So what you do, you just find out the coloring of this graph. If you find out the coloring and at every color, no.
So the adjacent should be different.
Right. Adjacent should be different. Yeah, correct. We just have to find out the colors. And at every color, since adjacents are different, so no, adjacents are time clashing, right? So suppose we have these 3 gates, right? Or else we can understand more. So here in this graph, what is happening? So this particular game has clash time with this particular game. So we cannot use the same computer to play this game and this game. We have to use the different one. And this is the condition for coloring too. We cannot color the 2 vertices using the same color if they are adjacent. But we can play the game whatever situated here, vertex number A and vertex number B on the same computer because their slots timing are different. So after playing the game number A, other person can play the game number B on the same computer. So for these 2 games, we can have a same computer. So at the end, you just have to find out the coloring of it. Okay. So what will be the possible coloring here? So again, whenever we have triangles or right, so here if you attach one color here, so suppose I'll attach red here. So we cannot color these 2 vertices with red. We have to use other vertex. So suppose I'll take black here and I'll take blue. Okay, but for this vertex, I can use either red or black. So suppose I'll use red for this vertex. Now for this vertex, I cannot use red, but I can use blue or black or anything. So I'll use blue for this vertex and again use red, and for this vertex I'll use black. So ultimately I just need 3 vertices to color this graph. So that means the minimum possible number of computers will be 3. I just need 3 vertices, 3 computers to play or to organize this particular event. Okay.
Yeah.
Any other doubt?
Excuse me.
Yes, please.
Ma'am, 10.7.
This one only?
Yes, ma'am.
Ma'am, if I have any doubt from week 10 or 11, can I send you on mails? This mail?
Yeah, you can send me on mail.
maths1 study dot. This is your mail.
No. You cannot send on this mail. This is not my mail. Actually, this is used for course. So I have other mail. So let you know. Okay. So first we'll solve this question. So here consider the directed graph. Suppose DFS of this graph is performed from node A. Obviously, they will give you a node from which you have to start. And such that when we visit a vertex, we explore its unvisited neighbor in alphabetic order. So see here also they have clearly stated which vertex you have to choose. So for example, if you have choice between B and C, you have to choose B first and then C. Okay, so which of the following options are correct? C, F is a forward edge and all those things, right? So first try to compute the DFS tree here. So we'll start with vertex number A. Now from vertex number A, we can go to vertex number B or vertex number C. You have to choose one neighbor. But since they have said that we have to choose in alphabetical order, we'll go to vertex number B. Now vertex number B is connected to C and D. So we'll go to vertex number C. Now C is connected to F only. So we have to go to vertex number F. And now vertex number F is connected to D. So this will be a simple graph. Now here, what are the non-tree edges? So forward edge, backward edge are only non-tree edges. So here the edge is CF, but CF is already used in graph. So that means it is not a non-tree edge. So it cannot be a forward edge. So the 2 conditions we have for forward and backward edge. First thing, it should be a non-tree edge. Non-tree edge means it should not be used in our DFS process. And the second condition is it should grow in the tree's direction. So here CF is used in the DFS process. That's why it's not a forward edge. Now FD. Now FD is also used in our tree, is also used in our DFS tree. That's why it's not a back edge. AC is a forward edge. So now AC is not used in our tree, and it is a forward edge because it is growing in the direction of tree. So this is the correct answer. And DB. So DB is also not used, and it is also growing in our fire. It is growing in our tree's direction. So that's why it will be a forward edge, not a backward edge. So that's why this option is correct.
Okay, ma'am. Thank you, ma'am.
Okay.
Okay, ma'am. Ma'am, I have one more doubt. Actually, it's in quiz 2. Can I ask now?
Yeah, you can ask.
I'll send you in chat, ma'am.
When the previous question is said, if I already used that, what is that?
If you use that edge in your tree, then it is not a forward, backward, or cross edge.
So which means already started. So we cannot form forward from there or what?
No, actually forward edge, what happened if you have a DFS tree, then whatever edges are in DFS tree, these edges cannot create a cycle at all because those edges are growing in one direction. So what we are saying, forward edge will be that non-tree edge which won't create a cycle. Yeah, I mean it is not related to cycle also. It's just an edge which growing in the same direction and also a non-tree edge, something like that.
Okay.
But it should be a non-tree edge. So for n term, the weightage I think will be 30 to 40%, or yeah, 30 to 40% from graph theory, and again 30 to 40% from week 8, 9 or 7, 8, 9, and remaining 10 to 12% from 1 to 6. We'll tell you the precise weightage in the revision session. Okay, so that's all from my side. If you guys don't have any doubts, you can leave.
I have a
Ma'am,
doubt, ma'am.
Ma'am, this is your last session with us in the regular sessions?
No, I think I'll take one more session because there are still we have 5 to 6 sessions, right? If I consider the mock discussion for then 6 sessions.
And the last week session, week 11 session, will take by Vishal sir.
I think so. He will take.
And week 9 ZA question number 2.
Question number 2 of what?
Week 9 GA graded assignment.
Yeah, ma'am, this is a standard question.
Maximum surface area of its curved surface. So a cylinder of radius x and height 2h is to be increased in a sphere of radius r, centered O, shown in the figure. The volume of such a cylinder is given by V is equals to 2 pi x square x, and the surface area of outer choose the set of the maximum cylinder. I think you have to relate the volume since here
Ma'am,
we
I
are
think
making sphere.
Ma'am, I think image is not shown in your desktop, in your screen.
Yeah, I refresh it, but still. Okay. So a cylinder of radius x and height 2h is to be in a sphere of radius r, center at O, as shown in this figure. So the volume of such a cylinder is given by V is equals to 2 pi x square h, and the surface area of outer curved surface is given by S is equals to 4 pi xl. Choose the set of correct options. So the cylinders has maximum volume amongst all cylinders which can be inscribed when h is equals to r. So the first option is kind of true, because if you increase, if you take any, because see here, right, so here what is happening that if you reduce the radius, then the volume of a cylinder is directly proportional to the radius. Radius is x and volume is 2 pi x square of h. Right? So if you reduce the radius, obviously volume will reduce. So the cylinder has maximum volume amongst all the cylinders, which can be inscribed when h is equals to r.
But it's not correct answer.
It's not correct. Yeah, because h is equals to r. I thought it will be ambiguous. Okay, so we can find out a counter example for this. See, if h is equals to r, then I can draw a cylinder which has a smaller volume. How? Simply take, so if h is equals to r, then simply take the value of x to be equal to 1 by r. Then what will be the volume? So volume will be 2 pi 1 by r square of h, which is equal to r, which is equal to 2 pi upon r. Right? And if you take h is equals to h, any number which is smaller than r, then this volume, then that volume will become bigger, right? So for example, you can create a cylinder like this, which has height up to radius, but the radius is very small. Right? Now this cylinder don't have the maximum volume. There exists some cylinder which will have a maximum volume, which will have a bigger volume from this cylinder. So that's why it's not free. Are you okay with the explanation? Since we can choose x anything, so we can choose an x in such a way that if h is equals to r, we will choose x in such a way that it will decrease the volume. So for example, if you choose h is equals to r, and if you choose x is equals to 1 by r, then the volume will be 2 pi by r. But if we choose h is equals to r and x is equals to r square, x is also equal to r, then volume become 2 pi r cube. Right? And this volume are different, and obviously this volume will be bigger than this volume, because here we are dividing by r, here we have r cube. So in the both cases we have h is equals to r. So that means it is actually not the case. If we have h is equals to r, then we will get a maximum value. It's not the particular case. Okay. Is that okay? So now let's go to the second option. So the cylinder has maximum value amongst all cylinder, which can be inscribed when h is equals to cube root of r. So if h is equals to cube root of r, so again it will depend on the radius too. So I don't know. Okay, so when we take h is equals to r by root 3 and h is equals to r. Okay, so sorry, actually I don't have exact explanation for this question. I'll let you know. It will. That's the logic.
It's a general question.
Yeah.
So if we are encountering a new question, if you haven't seen, or so how will you approach, whether you'll be seeing the solution or so, because whenever after theory part we are encountering the questions of it. So without seeing this, what is the actually usually students do and how they are approaching the problems? So what is the method for studying maths?
Yeah, see, so in general, what I do, first thing, there are two set of things, right? So one is the given thing to you. In any question, there are some given things. And the another thing is the result, whatever result you want to show, or whatever the result we can get. Okay, so sometimes the result is quite a clear if you have some options then, and sometimes we have to judge. But using these results, and again we have to find out some path or some logics, right? So from which come from given statement to the result. So here, whatever given to use, given is there, just think about all the result related to that particular thing. So for example, in the previous question, we have some volume pi, 3 pi x square and h something and some surface. So that means first I should be able to relate these two things. Okay. So
Okay.
that may give me some other information. See, and the sphere information too. And then whatever option is there. So as I do, in general, I try to find out the counter example if I feel that that option is not correct. Right. So these are the things. First thing, you have to remember all the facts related to the given information. If there are some information which you think is this is not related, or we are not using this information anywhere, so then we always, I mean, it's tough to solve such kind of question.
So usually students will do that. They'll go through the entire solution. After that, they'll trying to understand and they'll practice it.
Sorry, what?
The thing is, like, students will see the solution and they'll understand the solution. Then in the practice, and they'll
Right,
understand the pattern. Yes,
So when
that's
you
how it
see the
works.
solution, right? So when you see the solution, you should be able to find the logic that why he is writing that step after that particular step. What is the reason? So if you understand the reason, then you can apply that reason into some another question too. That okay, so for example, some step is here, and after one step they are jumping to another step. So you have to find out the reason between these two steps. That what are the logics they are applying. So because the concept will stay as it is, only the numbers or the formation of question will change. But whatever logic they are using from going one step to another step, that is important.
And the solution, if I analyze, some innovative things, they're adding it and subtracting and multiply that. So those also, it is beyond my imagination how to encounter. I mean, after seeing that only, because I will be stucking over there, because they'll be introduce some new innovative concept, like, yeah, this is we have to multiply. For example, if you're limit function, limit, when we are calculating, there is some methods. So rationalizing, so we have to rationalize, because that is beyond the imagination, right? So that and all, after we see the solution, we can.
Right, correct. Then you solve some questions, see the solutions, and then you'll get the idea, okay, this thing might work in other questions too.
Yeah, because if you solve the log question also, the same method actually yeah. So this is not, we have to make the base as same, then we have to do
Right.
such things.
See, one logic is there only, that we have to make the base same, then only we can apply all the properties and it will simplify.
Yes.
This is a one fact. That's why I say sometimes if goal is clear, then we can solve the question. That there we know that if we make the base same, then it may reduce to some simpler thing. Yeah,
Thank you.
a little bit of this. Okay, so what's your doubt in this question?
Ma'am, actually, in the first step, it is m to the power of log 2 to the base 3, but they have written as 2 to the power of log m to the base 3. How is it possible, ma'am? Only if it is m log 2 to the base 3, we can interchange the power, right?
Okay,
2
so
can
they
take
are written these two. Is that a property of log? So suppose a to the power log base b of x. So suppose this is sum equal to y. So what does this mean? So this means that log base b of x is equals to a to the power y. Correct? And this means that x is equals to b to the power a to the power y. Okay. And now let's take another way. So that means here they have changed m and 2. So when you change x to the power log base b of a. This is equal to, suppose, some other variable here. So z. Then it will become log base b of a is equals to x to the power 2. Oh, no, I have done some mistake on this. Yeah, I didn't understand.
They are taking 2 as common and they're just dividing that.
Yeah, now this step is clear, but why this quantity is equal to this quantity? That's her doubt. So see.
Ma'am,
So
there is a
M,
property, ma'am, that one, right?
yeah, is this a property? Then
Yeah, ma'am.
that okay.
M log 3m, so that we can change it.
That is not
so we
m
can change.
log, that is m to the power of log.
M to the power.
Yeah,
It's
yeah,
not
that's what
M
power
log.
only. Yeah,
Power
sorry.
only we can see. Okay. So that means
Can
this is
change
same
that,
as
yeah.
So let's try to prove this. So suppose we
Yes,
have
and we
some.
can take 2 log 3m common.
Yeah, then all things are obvious, but just one thing is not clear. So suppose this is equal to some quantity, so let's take it y. So then here I have to apply the log because this is a to the power, right? So if I apply log base b here, so then what happens? So suppose log base b of a to the power log base b of x. This is equal to log base b of 1. So then this is same as log base b of x. Now this will jump here into log base b of a is equals to log base b of 1. So we have this quantity, and I think we can prove this property. Just try to prove it the same way we have today. I think already we have a proof in lecture of this property. I remember this property actually. This is same as x to the power log base b of a.
Then is it one property, ma'am?
Yeah, it is a one property.
Okay.
In the lecture, I think they have mentioned.
Yeah, this is a property. We can swap that. Yeah. You can take log 2 also, no, as a base. Both the side.
Yeah. In place of b, you can take
log base 2. No, not this. Sorry, not here. The solution. So log base 2, we can take it out. So log 3m plus log 3m will come. Yeah.
Log base. Yeah, you can do that also. Because then this will become 1 and this will jump out. So, right.
Yeah, you can do that.
Ultimately, we are doing that only because here we have 2 to the power 3,
Yes,
2 to
yes.
the power log base 3. So the same thing.
Okay, thank you, ma'am.
Okay, then we can end our session here. Thank you guys for joining.
Thank you.
Thank you, ma'am.
Thank you, ma'am.